Okay, up until this time, we've talked about valence electrons doing the chemistry. That's part of the picture. There are electrons inside the nucleus as well that also do nuclear chemistry. So we're focusing totally on what goes inside the nucleus, what leaves and what comes. Okay, so um, so if we're looking at just the nucleus, that's called a nucleotide. As you know, it's composed of protons, neutrons, electrons, and about 30 other smaller subatomic particles, like musons and bosons, it's a whole bunch of them. Okay, these are the ones we're going to focus on, protons, neutrons, and electrons. Okay, the way we're going to notate the nuclear chemistry side, for example, we're looking at carbon. Look on the periodic table up here, it has 6 protons. And the most common isotope of carbon is 6 neutrons. So that's carbon 12. Okay, now the way we're going to write this is we're putting the number of protons on the bottom. And protons plus neutrons on the top. Now, if we look at an electron, now the scientific community says an electron has 0 mass. That is not true. It's very small, but it does have mass. Now we're going to talk about something that doesn't have mass in a second. So we can write an electron like that. Now, those of you who are taking notes on a computer are going to have a problem with the kind of the reverse superscript and subscript. The way I do that when I'm on a computer pad is I go like this. But anytime you look it up online, it'll look like this. Or if you're drawing it by hand. Okay, so we've got protons inside the nucleus. They have 1 proton and 1 proton on top with no neutrons. Then we have a neutron. Looks like that. And we have one more interesting particle. Who's heard of a PET scan? Any of you?
Yes.
Yeah, it's a very expensive one and very focused imaging. And it stands for positron emission tomography. That's the other particles, positron. Now, positron looks like that. So that's a positron. Now, as far as mass goes, I'm going to say electron has 0 mass. But it doesn't. It's 1/30,000th of a proton. That's why they call it 0. The problem with saying it's 0, though, is we have another particle called gamma. And that's pure energy. There's no mass at all. That's why I don't like to call electron 0 mass, because in the same time frame we're talking about gamma, which is truly no mass. Okay, and then protons 1 and neutrons 1. Okay. So these are the 4 particles we're going to be working with, subatomic particles. Now these guys come and go for guess what reason? Same thing I've been saying all semester. For stability. Now, in the periodic table, iron is the most stable, all the elements. So things get bigger, you get closer to iron. Things get smaller, you get closer to iron. So if you're down this end of the periodic table, to get more stable, typically you lose stuff. And the stuff is this 4 particles I talked about. If you're on the top part of the periodic table, you tend to gain stuff or capture subatomic particles. Now, nuclear chemistry happens every single millisecond of existence. It happens in the upper atmosphere like all the time. And we're protected from that radiation with the ozone layer and also our atmosphere. Because everything happens above us before it gets to us. Okay, so let's look at carbon 12. And we are going to lose, there's one other. There's one more. There's an alpha particle as well. And the alpha particle has got 2 protons and 2 neutrons. It's the heaviest of all the particles. Okay. When we say we have an emission, say a alpha emission, that means something is coming off the nucleus and it'll appear on the right side of the equation. So we're going to have, that's the alpha particle being emitted from the nucleus. And then what's left And what's atomic number 4 up there? The top number. What is it? Okay. I want you to look at something here. I didn't have to look at the periodic table. Because there's two things that need to be conserved when we have a nuclear reaction. Just like we conserved when we were balancing the equations, and we conserved the number of elements on each side had to be the same. Remember the carbons, oxygen, etc. Okay, so that basically with this, the top numbers have to be equal. So 4 plus what is 12? 2 plus what is 6? And now if we look on the periodic table, oh, that is beryllium 8. And this would be carbon 12. So a lot of times you just know what's being emitted or what's being captured. Now, the opposite of emission is capture. So say we had carbon 12 again, and it captured an electron. So this would be a beta capture because an electron is a beta particle. Okay, and what does that give us now? Well, that gives us 12 plus 0 is 12. 6 minus 1 is 5. So what is next on the left for carbon? Boron. So this is called transmutation. Transmutation is when the number of protons changes. Because the number of protons determines what the element is. So we've transformed carbon into boron. And remember, the reason why these reactions occur is for stability. So the boron 12 is more stable than carbon 12. Why? Because it decayed to that. Okay, so does that make sense on these reactions? Now, sometimes now, uppercase P is a proton. Sometimes there's more than one that comes off. So in this case, we have 12 plus 2 times 1 is 2 is 14. 6 plus 2 plus 1 is 2. Excuse me, is 8. Which is oxygen. So if carbon captures 2 protons, it becomes oxygen. In this case, oxygen 14. So, so the bottom line, whatever the nuclear equation is, top numbers have to be equal, bottom numbers have to be equal. Now, these are small particles we're talking about here. But for example, if we took U, the enriched uranium, uranium-235, and hit it with 2 neutrons, it blasts apart. Okay, so normally we would say, well, that's 235 over 94, which is what? Platinum, or plutonium, isn't it? 94. Oh, you gotta spell it right. However, that's extremely unstable, so that automatically breaks up to barium and krypton. And the sum of the protons and neutrons in each one of these has to be 235. And then barium is what, 56. And krypton is 36. And then this so the top numbers have to add up to 235. This is what a nuclear reaction goes through. So this is called nuclear fission. Because this, let me extend that. This is the part that's fission part. This part is not fission. This part is called capture. Sometimes they'll say bombardment.
You were doing subscripts on barium and
56 and 36.
even though it's the subscript above that or is 94. So I was curious if that.
But that's the most common isotope.
Yeah.
We can have very exotic isotopes in this. Yeah, I'm just saying though that whatever the number, top number is, it has to add up to 235. Okay, now, anytime you have a nuclear reaction, we have something that no one ever talks about, and we have that. That is gamma radiation. Gamma radiation is called ionizing radiation also. The reason why it's called ionizing radiation is because it will kick off, if it hits something, it'll kick out an electron and make it an ion. That's why it is very, very dangerous, gamma radiation. Down here for our nuclear. So this goes on in a nuclear power plant. And gamma radiation is given off. That's why the thing has to be extremely well shielded. Well, the other item that uses the same equation It's called a nuclear bomb. One is controlled, one is not. Except with Fukushima and Chernobyl. Otherwise, they're very, and 3 Mile Island also, up to that. They're very, very controlled because of, they don't want to waste the uranium-235, extremely expensive. And also they want to control the radiation being given off because things become more stable, that energy is also manifested in heat. So we have gamma radiation and heat additionally. That's not part of the balancing the equation. Every one of these reactions. And the heat part is why we do the fission to get heat to boil water, to make steam, to turn a turbine, to turn a generator, to make electricity. It's for the high pressure steam. Nuclear powered aircraft carriers work the same way. Nuclear submarines, they all have reactors in the back. My son-in-law was on a sub for 5 years or something crazy like that. And there are, for those of you who have been in the service, they rank your pay grade by an E number, enlisted number. The highest is an E9. So my dad was. He was in charge of the maintenance at Homestead Air Force. On a sub, there are 2 E9s. One in charge of the reactor, the other in charge of everything else. On a carrier, same way. The E9s run power of that ship. Now, on an aircraft carrier, they also power all kinds of electrical stuff. On the newest aircraft carrier, what's the name of the newest one?
Ford. The Ford.
Ford. It's got a whole bunch of extra stuff. It's electric. So when they built the generators on that carrier, they made them 3 times the size that it would require. Because they anticipated upgrading. And everything nowadays, upgrades required lots of energy. So if we summarize this, we can have so a nuclear reaction's got 3 parts. It's capturing or decaying. It gives off gamma radiation plus heat. Now, an atomic bomb, the heat causes lots of problems. We're just talking about a couple thousand degrees and a couple 100 miles per hour winds thrown in on top of that heat. So in the blast zone, quote unquote, all that happens. In a nuclear power plant, the heat is captured, boils water. The gamma radiation is contained in the nuclear power plant. Yeah.
For all of these nuclear reactions, there's an excess of gamma and heat for all of them.
Everyone.
Okay.
And if you look in your textbook, it never lists that. Because it's not, doesn't, none of those, the heat doesn't have mass, the gamma doesn't have mass. And they never list, I don't know why, but it's always there. As you know, you look at a nuclear bomb. If whenever they show the reaction for a nuclear bomb or a power plant, they mention heat, and they don't mention this part of the reaction. And also don't mention the gamma. problem. So I was just telling him, China has built the first in the world thorium nuclear power plant. It's not, it's not, it's not powered by uranium. It's powered by thorium. Where do you get thorium? From the sea and sand all over the place. And the Gobi Desert in China is a big, giant desert. So they got one running and it's working pretty well. Ahead of the United States, ahead of Europe, ahead of everyone. It's pretty cool. Now, thorium's got a lot of advantages. It's a much safer reactor than uranium. Also, you don't have to stop the thing when I'm going to talk a lot on nuclear reactors probably tomorrow. There's some problems. One of the cons of nuclear reactors is what happens when the uranium-235 becomes lower and lower and lower and isn't producing as much heat. Well, it takes about 20 years for that to happen. Then you've got to go into port and you've got to swap that out with some fresh stuff. Thorium does it 24/7, a little at a time, because it's a liquid rather than a solid. So it's really much more efficient. It's safer because you can contain the stuff better. A lot of good stuff. It also produces heat and gamma radiation, like all the nuclear reactions. Okay. Now the alternative lab 15, which is totally extra credit for you guys, goes into measurement of radiation. You know, typically you all have heard of a Geiger counter, right? And it goes click, 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 click. It goes click, 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 click really fast when you get near. And it's measured in variant, there's reams and there's all kinds of measurement ways to measure radiation. And the lab goes into that in excessive detail. Now, one of the problems with nuclear anything is the gamma part. So during the 50s, my dad was in the Air Force. We moved around Air Force Base to Air Force Base. And when you get to your new destination, because of my dad's rank, we'd always get base housing. And the problem is your furniture never kept up with you. It was always about 2 or 3 weeks or even a month behind. So I was in my room with nothing in the room, a sleeping bag on the floor. That was it. And a suitcase. Well, I had nothing to do. So on all base housing, they had these packets. And the packets were full of material in case of a nuclear bomb exploded close by. How to build a fallout shelter, all this stuff. So that's what I did. I read that. Because I didn't have anything else to do. And every base had the same stuff, so I could read the thing, all this stuff. And so one of the things they talked about was, how do you protect yourself? How do you keep that bad fallout's nuclear radiation dirt that finally comes back, settles back down, which is part of a dirty bomb, by the way. How do you protect yourself from that radiation coming off of the is to build a fallout shelter, and that fallout shelter has got things to absorb the gamma radiation. Now, if we go back up here, we have another column called strength. Okay, so. Gamma's strong. Bless you. Who knows where they got the term blessed from? I learned this about a week ago. Comes from the Middle Ages. Anyone have any ideas? Okay, they believed at the time when you sneezed, it opened up your soul. And it exposed your soul. And that's why you wanted to bless the sneezing to keep close. And my friend is from Scotland, his name is Bigo. And he was training to become a Jewish rabbi when he was younger. So there's all these little stories on him. And so much fun. He's my chess partner. He and I play chess. It takes us hours because we're always chit chatting. But his wife, we play out on our. He lives 2 apartments down from me. We play out on the walkway between the two, and sometimes have refreshment. Anyway. Okay, so the stronger the radiation, the more you have to put between you and the source of the radiation. Now, with gamma, we're talking about concrete. Alpha is interesting. It's weak and strong at the same time. Because of its size, it doesn't go very far. It's like a 18-wheeler versus a Ferrari. The 18-wheeler is like Alpha. Big, cumbersome. And the Gamma is like the Ferrari. So it's strong, period. So Alpha, because it's so slow and doesn't go very far, you don't need much protection. Paper will protect you from alpha radiation. Now, who has a smoke detector in their house? Gosh, you're all raising your hand, right? Inside the smoke detector is a little can with a hole in the top. And there is an alpha emitter in there that runs through, and on the other side of the little hole is a detector. So when smoke comes along, it interrupts that flow of alpha particles and the alarm goes off. So if you ever take apart the smoke detector, don't, because there's alpha emitter inside that can. Now, who's into spy novels? Anyone? Okay, back in the KGB days, there was a famous person killed. Person happened to be a double agent for the Britain and Russia at the same time. And no country likes a double agent. It's a lose-lose proposition for both countries. So they decided to get rid of it. So what they did is they did a James Bond 007 kind of dinner, you know, with black tie, black tux, with the fancy bow tie and all that stuff. And they gave him this lavish dinner. Inside the lavish dinner was a bunch of alpha emitters. Now, go back to the slow and strong at the same time. Alpha particles don't go very far, but if you're in their way, you get the ramifications of a 18-wheeler. It's very strong, short distance. Well, put it in the stomach, guess what? There's no paper there to stop it. It was right up against the stomach wall and all of his organs there. And he died. He died a horrible death. Radiation sickness is a bad way to go. He was so radioactive, they took a special hearse taken to his grave. In the hospital, he had to have two isolation rooms, one inside the other. It's so radioactive. And it was because of alpha poison. Another poisoning was done with the tip of an umbrella. Also Cajun. And this person just got nipped with the tip of a sharp umbrella. And introduced an alpha emitter into the body. And what did he want to do? Hard to prove. Hard to prove. It's a really bad thing. So anyway, your house had these alpha emitters inside the smoke detector. And they are a pain. If I leave my door to my bathroom open, I take a shower, it goes off. If I'm frying something in my kitchen, they go off. Okay, so a lot of fallout shelters defend against gamma radiation. So they have usually concrete. The more dense the material, the better. Also, they use lead. Lead's a lot more expensive than concrete, so they usually use concrete. Now, if you work in a lab with radiation, you're a lab tech or you're an imaging specialist, you've got a badge here. If you're on a nuclear carrier or if you're a nuclear submarine, you've got a badge here. That tells, and it's wireless, that tells the medical facility there how much radiation you have absorbed. And they have a limit. Can't go over the limit. And it's important to have that there. Who's watched the series Chernobyl? Anyone? It was well done. Huh? It was excellent. Was it 5 or 4 seasons? I forgot. Episodes.
So it's fine.
Yeah, the science is pretty accurate too. First responders died within days. Horrible. And the problem with radiation sickness when you get it, morphine doesn't work. Because the receptors are messed up by the radiation. Your opioid receptor. It's horrible. Anyway, that's one of the reasons Russia, the USSR came down, was because of Chernobyl. The mismanagement of it, number one, and the politics around it's amazing. That part that I found interesting was politics screwed everything up. Now, I recommend that to anyone. It's gruesome, got some gruesome parts, but it is very interesting what's going on from a political perspective. If you're interested in that at all, highly recommend it. Okay. So the stronger the discharge of the particles, the more dense and the material is to stop it. Okay, so now what you're gonna have to do, by the way, your practice test and your take-home problem are posted. Posted that this morning. It was like I got up and I'm like, oh, I forgot I was gonna do it last night. I forgot. So anyway, it's posted, bottom line. Then I was just looking at it. The problem is on the last couple of problems on the practice test, the images didn't come through. Only part of the image. So I'm gonna post that separately. Basically, it's a picture of a nuclear power plant, both nuclear and coal-fired, and you have to explain how it works.
Maybe
Did yours come up okay?
yeah.
You have it there now?
What?
Could you pull it up?
Yeah. Here.
Yeah. It looks like it's pretty fine,
Yeah.
but when you do it, you won't see it. One part of it is weird. Well, that's printed. Yeah, printed. Yeah. All right, so that's the intro I wanted to do today on nuclear chemistry. The tomorrow we're gonna cover half-life. Who's heard of half-life? Anyone heard? Okay. What do you think it is?
I think it has something to do with like decay of the.
Yeah. And when decay happens, what happens to the original mass? Does it go up or down? Down. So there's initial mass, final mass, and the half-life. Now, half-life is directly proportional to stability. The more stable a compound is, the longer its half-life. The shorter the half-life, the more instability that particle has, it wants to become more stable. And that's a time unit. It could be decades, or it could be nanoseconds. Now, a lot of the man-made, person-made, I should say, they always call it man-made, particles past uranium, the ones in, the mass is in parentheses, like plutonium and, plutonium, anyway, those are all, very unstable. That's why they're in parentheses. And we'll just talk about that tomorrow. Now, there's two ways to do this problem. There's a fancy mathematical way, using logarithms, and a nice graphic way that I invented. That's what we're going to use, the graphic way. I just want you to understand the concept. Because the math gets in the way. Like a lot of math gets in the way. Okay, that's it for today. And again, I want to remind everyone, Zoom session tomorrow. We're going to beat this heat. And I don't know, and we'll see how Thursday plays out. We may be zooming on Thursday. The lab schedule was done to take the gas lab, dry lab, and split it in half. And do the project work each of the two labs. So there's, which is lab 11. So 11 and 12 are to be done this week. Now, lab 12, I gave an alternate. I think that's what you were doing, right? And then your project you're already working on. So that's why it's 2 days, and I'm required to follow the lab schedule. I can do alternate labs, but I have to do the schedule. So that's what we're doing this week. So dry labs the whole week, wet labs next week. There's gonna be 2 wet labs next week.
Yeah. First round.
Okay, any other questions?
This is the project.
See everyone tomorrow.
It's a lot of, it's a lot of.
They turn in there.